Okay, so let's go over something that everyone hates, or really likes, if you're me, is scalar line integrals. And so, the thing about scalar line integrals is that they're really unintuitive for the reason that no one likes to explain anything right in calculus. Okay, well, hopefully I can do a better job. So, this is what you do in one-dimensional calculus. You say this is an integral. An integral is the area of the graph of this function.
The area under the curve.
Yeah, that's the problem, because everyone thinks a function is a curve, except the graph of a function is a curve, not the actual function. Okay, so we'll see why this makes more sense when we go into line integrals more in depth. So, okay, this is what everyone thinks when they see an integral. Okay, well, great. But, you know what? If I have something living in one dimension, I shouldn't have to force myself to go into two dimensions to kind of compute the integral. So really, what everyone was doing back then was a line integral where f of x still lives in the number line. And we're going from, oh, I should move my 0 over here, x1 to x2. And what we're doing is adding up a bunch of little f of x's here, 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 all the way down the line, and getting a sum. And that is how we integrate in one-dimensional calculus, okay? But we represent it like this. But if you look at it carefully, this is really just a line integral. It's a directed integral from a to b, summing a lot of stuff up. Okay? So, what's the difference between these line integrals in one dimension and line integrals in two dimension is, well, this thing is pretty straightforward in its length. Look, it's perfectly straight. But now let's try something different. And this one I'm not going to graph. This one I'm just going to show the space that it lives in. Because you know what, graphing in 3 dimensions is a lot, and you can't graph in 4. So if you have a 3-dimensional variable, you're never going to be able to graph it. So you have to kind of think of this in the place that it lives. Okay? So this is x and y. We have a function of x and y. Okay? That's it. So say we want to integrate a line integral from here to here, like that. Well, in one-dimensional calculus it was easy. We just have a straight line. In 2 dimensions it's not so straightforward. Okay? And so we can do something called parameterize the curve, and we'll go over that. So this is kind of the reasoning behind doing a line integral. You're still adding up little chunks of f of x as we go along, just like we're in here. And so that's what the notation means. What we do is take the integral.
That looks like a weird S.
That's an integral. Thank you. Except now, x1 and x2 are either vectors or points, whatever you want to think of them. Well, vectors are points if you want to think of them that way. So we can put vector symbols over them, or we can choose to go from point 1 to point 2. But we write the same thing in the middle. F of xy, and then we write this ds thing. Okay, and we'll go over what the ds thing is later, because it's a little bit complicated. But ds is basically a length element. The difference is the length element in one dimension always stays the same, and the length element in 2 dimensions doesn't, because we've got some curvature, it's not straight. And so that's the real concept behind scalar line integrals, and actually vector line integrals as well.